All right, I guess so that I don't have to trim the video file too much, I'm just going to go ahead and get started. Welcome to the talk again. Basic prerequisites. Honestly, I guess a first class in algebraic topology would probably be ideal. The more you're willing to black box, the more you can do with this, I guess. It really is sort of about the computation, so knowing homology and stuff is helpful, but I won't stop anyone from watching, I guess, if they want to go through it. Other than that, we can get started. So the object of today's talk is we're going to do a very simple goal. We're going to try to fully compute Pi4S3. In order to do this, we're going to need to build up several slides of machinery and probably talk about stuff at a very high level for at least an hour. The goal of this talk is to present a spectral sequence computation that is both sufficiently complicated to give you an idea of what it's about and why these things aren't trivial, but also to, at the same time, paradoxically convince you these are doable. It's a lot of data, but if I am like methodical and I just go through them and try to like be creative, these computations are accessible and doable. Because I feel like looking at a definition of spectral sequences just makes you want to like die on the inside. It's incredibly complicated and there's a lot of degrees to pay attention to and stuff. So I've included a bunch of like pictures and graphs that I hope will make this more interesting. Okay. All the methods here are developed in Serre. My main source is going to be Ravenel's book, Complex Cobordism and Stable Homotopy, I think is the title. I think people sometimes refer to it as like a little some color book, but I think the color is also not the actual color of my copy, so I can never remember it. Okay, just some conventions. All spaces are going to be finite path-connected CW complexes, unless that's obviously not true. I don't think I'm taking any disjoint unions or anything in this talk, so it should be fine. I think this assumption is fine. By based, I just mean that spaces have a base point. So if this is my space, I just have some base point. All functions, all continuous functions are going to be, so all functions between topological spaces will be continuous. All continuous functions will respect the base point, which just means like f of the base point is the base point in the other space. If you see a map between algebraic objects, it's a homomorphism, et cetera, et cetera. Again, if X is a space, I'm just going to use like lowercase x0 to name its base point. If Y is a space, the base point will be lowercase y0, etc. I think those are actually the only two letters I use for spaces with important base points. H star X will refer to its singular cohomology with integral coefficients. This will make the notation significantly less painful to look at. And if I need to give you a different coefficient system, I'll do something like, you know, H whatever X semicolon some group of coefficients G or ring of coefficients G. Okay, so those are the main conventions for this talk. If you feel like I'm missing a technical assumption or something, feel free to ask. To be totally honest, I won't guarantee that I can answer them all live, but I will look into it for anyone who wants to know more specifics about any of these results. On the other side of that, a lot of these results are not stated in their full generality. I'm aware that they're not stated in their full generality. It is not helpful, I think, in this talk to do that, so I'm not going to. But if you are aware of it, it's something to keep in mind, I guess. Section 1, fibrations and fibers. So fibrations are, in some sense, a similar notion to, you know, fiber bundles, vector bundles, whatever have you. They're surjective maps from X to Y. The term Serre is important. There are actually two types of fibrations. I think the other one is usually called a Killen fibration. I'm just going to call them fibrations from here on out, but know that this is the Serre convention. And they induce different model structures, if you know what that means. So explicitly, a fibration is a surjective map where homotopies in the target space lift to homotopies in the above space. What this really means is that we have two pieces of data to start with. So we have a homotopy H, and that would be this guy right here. So we have some homotopy happening in Y. Now, what we want that to do is we want to lift that to a homotopy in X. Obviously, without any more information, this doesn't really make any sense. So we also want an initial lift H0. And what I mean by that is the homotopy has a function at time 0 and a function at time 1. We want a lift of the function at time 1 to X right here, so that if I compose from A to X to F through F to Y, this gives you the original like H0 function. So yeah. And given this data, any map, a map is a fibration if we can always find some dotted map here that lifts the homotopy from this initial lift H tilde 0 to, basically H tilde 1, and that this all like respects commutativity. So, you do the homotopy downstairs, you lift up to X, you do the homotopy there, and then you go back downstairs. All of this commutes. We actually won't be using this property a lot, but I figured I would at least tell you what it actually is. Okay, so these are fibrations. Now, what maps are fibrations? If you're a homotopy theorist, the answer is all of them. To be a little more precise, given any map X to F, X to Y, we can fatten X a little bit so that this map can be, surjective by creating the space NF. So X is going to be weakly equivalent to NF, meaning that all of its homotopy groups, all of its homology groups are the same. And then the induced map NF to Y is going to end up being a fibration. The details of NF are down here. If you don't know what any of these spaces mean, it's not a big deal. Just know that intuitively NF sort of fattens X so that the map can be surjective. And this composite is on the nose. So taking the weak equivalence and then the fibration is exactly the same as taking F. And so we're going to be replacing maps with fibrations a lot. For the most part, it doesn't make a huge difference whether or not you think about a map or its replacement, with one small detail, which is going to come up. Okay, first, fibers. So this is just the traditional notion of a fiber. Preimage is another term people use. I'm not entirely sure why topologists tend to use the word fiber, but I do like it more, so I'm going to. Specifically, if you remember, all of our maps are based. That means that the target space has a base point. So when I say fiber, what I really mean is fiber over the base point. And this means that for any based map, the fiber is well-defined. And then a nice theorem about fibrations is actually, regardless of what base point you choose, all of your fibers are going to be homotopy equivalent. So for any normal map, I have, the target space Y, and I just take the fiber over this map to get like P-1 of Y0, or F-1 or whatever. For a fibration, I could actually, for a connected base space fibration, I can choose whatever of these points I want, and it ends up giving me the exact same fiber up to homotopy, which means we don't have to think too hard if we're using a fibration. But again, these details aren't really that important in this talk. But because these fibers are well-defined, we normally package the data of a fibration by saying not only the fibration itself, but we also include this fiber over the base point as well. Just some nomenclature: X is normally called the total space, and Y is normally called the base space, in analogy again with fiber bundles, vector bundles, what have you. Example. So this is a very important example. Let Py be the set of sort of based paths in Y. What I mean by that is if this is Y, then the elements of Py, and this is the base point Y0, then the elements of Py are all paths that, look like this, and maybe, they come back to each other to form loops, but they can do whatever, as long as they start at the base point. If you paid attention to the NF construction earlier, this is a little bit different because those paths did not have to start at the base point, which is why these two don't end up giving you the same thing. If you think about it, so there's a map from Py to Y. What we do is, again, given some paths, this is Y0, this is gamma, this is where gamma ends up at time 1. We just take gamma and we send it to gamma 1. This is a path, in fact, a fibration from Py to Y. And just thinking about the fiber, what is it? Well, it's paths that end at the base point. So it's loops, sorry, I forgot to define this. This is just based maps from the circle to Y, where it doesn't matter what base point you choose for the circle. So yeah, these are going to be important examples of fibrations. Another thing to think about, which should become obvious a little if you think hard enough, is that this space should be contractible. And what you do is you just take any path and you just shorten it. And this will be important for one of the exercises at the end, but doesn't really matter for our purposes too much. Okay, homotopy fibers. So I've given you a bunch of details about fibers. Hopefully that was mostly review. Homotopy fibers, I don't expect people to come in knowing. So let f from x to y be any map. Y and x subject to the conditions I normally put them on. Then we can form its homotopy fiber, which I will denote as FF for most of this talk. Eventually I will drop the little f because I'm lazy, and it would make notation even more painful. But it's going to be the pullback of this diagram here. You can see the explicit definition right here, or you can just think of it as, this is the path space fibration, by the way, so you have your omega y sitting up here. Sorry, loops y. I always think in LaTeX for some reason. So this homotopy fiber is going to be sort of a homotopy analog of the normal fiber. If you think of homotopy theorists as people that freely replace maps with fibrations, you can think of the homotopy fiber through this theorem as being just a homotopy analog of a fiber. And what I mean by that is that there's a natural inclusion here, which I write down right here. And this is a homotopy equivalence. So if your map is a fibration, then you can take the genuine fiber, include it into the homotopy fiber, and this is going to be a homotopy equivalence of these two objects. So for fibrations, if you're trying to do like algebraic topological computations, working with a homotopy fiber is the same as working with a fiber. This isn't true for maps in general, which is one of the sort of reasons why, as much as I like to pretend that everything only matters up to homotopy, occasionally you do have to think about whether you're using a map or its fibration. This is a fun exercise someone can do. Basically, one way of producing the homotopy fiber is to take this pullback. Maybe a more intuitive notion, which is sort of flavored by this theorem here, is that you can take a map, replace it with a fibration using the NF construction from before, and then the genuine fiber of the map from NF to Y will be the homotopy fiber of the original map. So really it is sort of like a homotopy theoretic analog of fibers. Okay, now we're going to talk about fiber sequences, which is one of the last things you need to think about in terms of fibrations and fibers. So given any map x to y, one can just adjoin the homotopy fiber just like before. Then there's a natural map from omega y into FF. Let's call this inclusion I, or I do that down here. Yeah, so there's a natural map from omega y into FF. There is a map called, so given a map x to y, and given the spaces omega x and omega y, there is a map called omega f. This is just a functorial construction. And the idea is what you do is you take like a map from S1 to X, you got a map from X to Y. Oh, look what you do. You got a map from S1 to Y by post composition. This negative sign just means that not only do we take that post composition, but we also reverse time, which ends up being sort of important for technical reasons, but won't again come up in this talk really. The really important thing about this, and the thing that is very hard to really imagine, is this part right here. And what it's saying is that for these pairs of maps, each one is basically a homotopy fiber projecting onto the domain, and then a fibration. A homotopy fiber projecting onto a domain, and then the map of that homotopy fiber. Which allows us to do computations by like starting with a map x to y, taking its homotopy fiber. Turns out the Serre spectral sequence allows you to play with this, but maybe you don't know enough about the space y, but you do know something about omega y, or maybe you don't know anything about the fiber, but you do know something about y and its loop space. Then you're going to be able to sort of like shift your lens to look at those three spaces instead, which is exactly how we're going to do the computation at the end. Okay. I've just said a lot of things. Let's review what we've learned. First is that all maps can be replaced by fibrations up to homotopy. This means that even if we start with, a garbage map from X to Y, we can replace it with a fibration and try to use it to compute homotopy groups and homology groups and stuff like that. The second is that all maps have a homotopy fiber, and that this homotopy fiber agrees up to homotopy with the genuine fiber if the original map is a fibration. And finally, we can create these fiber sequences for these maps. And all of these tools will be useful in the following computation. So I've just said a lot very quickly. I want to take a short break and see if anyone has any questions about the previous stuff. And I'll sort of scroll back and forth depending on what people need. But if there are no questions, I guess I will just keep going. Take a drink of water for myself.
What's an example of a fibration?
So you have your standard fibration that I gave before, which is just like you have a space Y, you have its path space, and what you do is you take a path and you project onto the endpoint. So like if this is Y, this is base point, this is path, I just send the path to the point where it ends at, kind of like a treasure map, I guess. And this fibration has homotopy fiber or normal fiber up to homotopy, it doesn't matter, loops on Y, which is just maps from S1 to Y. There's another example of a fibration that's very famous, which is called the hop fibration. This is a map from S3 to S2 with fiber S1. You can construct it in a bunch of different ways, but this is actually essential in proving that Pi4S3 is infinite cyclic, which was, if I'm remembering correctly, the first example that showed that. So at the very beginning of this whole game, people really wanted this to be true, because it's true when because it's true when m is less than n. They were like, oh, spheres are nice, they should play well. We're just talking about maps between spheres up to homotopy. Hopefully all these higher groups are zero. Turns out they're not zero. So you can ask, are they all finite? Turns out they're not all finite. And this was a counterexample to that. In fact, we're also going to show that there are finite ones a little bit later on. That's sort of the goal of the talk. Are there any other fibrations that I want to? Oh, there's another fibration. So I'm just giving you the three from the exercises, which is SU n-1 to SU n to S2n minus 1. This is actually a really nice fibration because it allows you to completely compute the cohomology ring of that guy, like including the multiplication structure, which is really cool. And actually, this was the first example I worked out on my own of a spectral sequence. And it was a bit painful, but very fun. And I would recommend it. So all three of these are exercises in various ways that I have at the end. All right, are there any other questions?
Yeah, so, excuse me.
Go ahead, Brandon.
Sure. So if you go back to the fiber sequence, when you say each consecutive pair, are you talking about the consecutive pairs of maps here?
Yeah, so
Okay.
just as an example, I guess you would have like omega y to ff to x, and the claim would be, the claim would be that omega y is equivalent to fi. Yeah, so it's the homotopy fiber of the map I. And the claim is that this works for all these. I really didn't want to prove this, but you can find the proof in Peter May's Concise. That's at least the one place I know where to find it. All the details that Ravenel leaves out are in Peter May's book, I think, up to a bit of Googling.
Am I correct in assuming that locally trivial fiber bundles are an instance of fibrations?
Yeah.
Okay, so but it's more general because we only know the fibers up to homotopy, right?
Yeah, that's sort of the idea, is that so you can do all these things using only fiber bundles, and actually a really key intuition for the Serre spectral sequences E2 page, which I'll explain what that is in a bit, is exactly fiber bundles, because it works like you would expect it to work for fiber bundles. And I guess the sort of idea is like, up to homotopy, this sort of local triviality condition is a bit strong. It's about like local homeomorphism. And all of the invariants we care about are homotopy invariants. So maybe the intuition is like, yeah, fiber bundles should work, but something more general should also work as well. And likewise, fibrations end up having that homotopy fiber thing. That that all the fibers are homotopy equivalent. But importantly, that's not the definition, and that's a theorem. And the definition of a fiber bundle is entirely homotopical. It's about like lifting homotopies from spaces.
Yeah, I'm just trying to get the mental map right, because all my examples are like local trivializations, and then this general thing is all these path or loop spaces. But I cannot, for the love of God, imagine a loop space. It's so this is kind of my problem. I want to be a bit more general as an example than
the
fiber bundles.
Cheating example of a loop space is that if you know what homotopy groups are, if you take the homotopy, so you start constructing Pi1, but what you do is you stop before you say homotopy, and you instead topologize it. All of so the pre-homotopy version of Pi1 is up to giving it the mapping space topology, the loop space. It's hard to give you an example because, so maybe people are familiar with the fact that like sigma Sn is Sn plus 1. So this is the suspension. This acts really nicely, but loop spaces of spheres are not lower dimensional spheres. So it's difficult to give you, like, I'm trying to think. I only know like a little bit algebraic examples, one of which will come up, but in general, I don't think that loop spaces are super visual. In fact, they're actually very algebraic, because like being an n-fold loop space ends up being like very related to how homotopy commutative you are in terms of like being like having like a multiplicative structure. So like it's hard to think about it geometrically. So it's not your fault that it's hard to picture it, I guess, is my point.
Okay, thanks. That helps a lot.
Are there any other questions? Alrighty then. I think that was pretty good. So we will move on. Section 3 is spectral sequences. The next slide is intimidating. I'm going to recommend that people only pay attention to the parts I highlight. There's a lot of text, but that's mostly because I want these slides to be something you can reference without me being there. Okay, spectral sequences. This is the data of a basic spectral sequence, all written very concisely. The idea is as follows. You have pages, which we call ER, so E1, E2, E3, etc. And on these pages, you have this sort of integer grid where you have for each P and Q, an abelian group or some object in an abelian category. We're just going to use abelian groups, or I guess also kind of rings. But so for each P and Q, you have an abelian group, and we're going to denote this EPQR. What this means is you go to page R, you point your finger at the PQ spot in the grid, and that's going to be an abelian group. Not only do you have all these groups, but you also have these differentials that are relating them, and these satisfy, your normal condition. Dr squared is 0. What I mean by that, of course, is you take the ones where it makes sense to compose them. If you compose them, you get 0. And so you have all of these objects on each page. Within each page, you have all of these maps connecting them. And then the final important thing is that to flip from one page to the next, you just take cohomology everywhere in sight. So what this amounts to is a bunch of pages of abelian groups with an integral grid of groups, a bunch of differentials between them. And in order to go from one page to the next, you just take cohomology. That's the intuition. Now we're going to look at some pictures. So this is what the E1 page looks like. Very boring, not too interesting. You got your P axis here and your Q axis here. So our spectral sequences are going to be R and negative R plus 1 graded. What that means is that something in PQ is going to get mapped to something in P plus R, Q minus R plus 1. One important thing to note about this convention is that P plus Q gets sent to P plus Q plus 1. And this ends up being a very natural condition to impose. Or sorry, this ends up being a very natural condition to impose. So example, if R is 1, this is 1, that's 0. So you're just going straight horizontal. All right, now let's get a little bit fancier. I start to get lazier with my arrows with each page. I apologize for that, but it did take a while. So now what's happening? Well, P is now getting mapped to P plus 2, and Q is now getting mapped to Q minus 1. So Q minus 2 plus 1 is going to be Q minus 1. And so what's happening is just your basic elementary school rise over run. We got all these maps going like this. And each of these dots has a map. And the reason why I'm drawing only one quadrant of this grid is that for the Serre spectral sequence, you're mostly only concerned about spaces and their homologies. So anything that's like in negative degrees is going to be 0 by convention. So this is where our action is going to be happening. And so you just got these maps. And then E3, same deal. You've got maps going like this, et cetera, et cetera, et cetera. Again, there are a lot more dots and a lot more arrows that I'm drawing. Okay. We often start by giving the E2 page. And the reason for that is that the E1 page will be like some cochain complex that we understand decently. So we know exactly what the E2 page is, so there's no reason to write the E1 page. The Serre spectral sequence, for example, the E1 page would be like singular cochains with a certain coefficient group. And then the E2 page is just cohomology. So you just start with that page. Okay. Now we're going to talk about convergence of spectral sequences, which is probably the second hard part if the first hard part is computing the DR maps. Oh, I was supposed to give some intuition for that. The reason why computing the DR maps is hard is like, yeah, we have a very constructive notion of how to build a spectral sequence in some sense. But also, if you're familiar with connecting homomorphisms, computing them is a huge pain. Computing DR is like way worse, which is why I think if you look at the Bockstein spectral sequence, the DR maps end up actually being connecting homomorphisms or something like this. Okay. So you have, okay. Now imagine for a second, we're looking at this page. And like I said before, with our conventions, normally everything to the left of this pink line is going to be 0, and everything to the bottom of this x-axis is going to be 0. But imagine also that like you have some bounding line like this. It doesn't have to be straight, it doesn't have to be whatever, but imagine like everything here is bounded. Well, then what's going to happen? The DR maps keep getting longer and keep rotating more. So in particular, eventually the maps will be like, here, let me switch to a color, will be something like that. So all the outgoing maps are going to end up in the out of bounds area, and all the incoming maps are going to end up in the out of bounds area, which is going to mean that like the maps are going to a 0 group, which means they must be the trivial map, or they're coming from a trivial group, which means they must be the 0 map. So if all the maps are 0 maps, then taking cohomology doesn't change anything. And so what we end up getting is that if eventually all the DRs are trivial, it doesn't have to be because of bounded reasons, but bounded reasons are a good one. If all the DR maps are trivial, eventually taking cohomology doesn't do anything. And so flipping the page just is the same page over and over and over again. If this happens, we say that this page where all the differentials are 0 is called the E infinity page, just to note that it's converging. And a spectral sequence is said to converge to something called A star, which is just like a graded abelian group or something like this, if AN is given by taking sums along the diagonals of the spectral sequence. So the areas where like P plus Q equals N is something like that. Yes, I think that's right. So you're taking sums along these diagonals, and that's giving you back the object that you wanted to start with. If that happens, the spectral sequence is said to converge. Now, in the actual construction of a spectral sequence, you're actually taking a filtration of this thing called A star, which means that when you try to get A star back out from the spectral sequence, suddenly you have to deal with like extension problems. But that won't come up in today's example, so I'm not going to get into them. So yes, just a review, you have a spectral sequence. What that is a bunch of pages of data with abelian groups in all sorts of places. And that for all of these abelian groups, you have differentials relating them. To get to the next page, you take cohomology. If eventually there aren't any more pages, you've basically come up with your result, modulo extension problems, and you have computed your object. So the way to think about this is like, hey, maybe computing A star is really hard. Maybe A star is like some homotopy group. Maybe it's a really hard cohomology group for some reason. Maybe we just don't know how to compute it. But maybe we can like break it into smaller pieces or something and relate those smaller pieces in a way where you can compute everything involved. If you can do that, that's sort of the idea of a spectral sequence, is you drastically overcomplicate your problem in terms of data, but in terms of each individual computation, make it way easier. And then you combine all these computations at the end to get your result. This is actually a really common phenomenon, not just restricted to spectral sequences. Like in terms of localization, you can compute P components and then combine them all, stuff like this. So breaking down a problem and then combining it at the end is very common in these types of algebra. Okay, visualization. Oh, this is where I was gonna show you like, yeah, the maps are gonna start getting too big. Upshot. So what's our goal? We're going to have an E2 page. Hopefully this E2 page is something we can just compute right away. We're going to try to figure out what the differentials are and flip to the next page. And we're going to try to keep on doing that until eventually we run out of pages. Once we've done that, we're done. So the big goal is to get all the DRs to eventually be 0 and to figure out what all the lower ones are. Which brings us to our actual computation for today. This is a method developed by Serre that combines the first half of the talk with the second half of the talk. And what ends up happening is you try to compute the cohomology of a total space by combining the cohomology of the fiber and the cohomology of the base space, which is where this intuition about fiber bundles is coming in. Okay, let f from E to B. I changed my notation here a little bit. I was using X and Y before, but whatever. I guess that's confusing with the E pages. Oh well. Let f from E to B be a fibration with simply connected base space. You can actually weaken this simply connected assumption to simple, which means that like the fundamental group acts trivially. Or if you want to get really complicated, you can use like local coefficient systems and do all of this for even nastier setups, but we don't need it because spheres are actually very connected, in fact. So suppose you have the starting information, then you have a spectral sequence. The E2 page is this. Now, the intuition from earlier that I wanted to state is if you are aware of the universal coefficient theorem, you have HPB with HQF is up to torsion issues HPB times HQF, which looks a lot like a local triviality condition. And in fact, when you know that this torsion doesn't exist, some authors will even present this as the E2 page. But I don't think this is a very good convention because I don't think that this is particularly harder to compute. Okay, so this is your E2 page. It's very much inspired by fiber bundles. You have multiplication induced by the cut product in cohomology. This multiplication is just additive on indices. So EPQ times EQ, P prime, Q prime goes to E, P plus P prime, Q plus Q prime. And I'll explain why this is induced by the cut product in a second. And very importantly, the DR respects this product in terms of being a derivation. This looks a lot like a chain rule, except you have like this extra little guy right here, which is just like a sign issue when you're working with these like graded objects. Okay, so what is the multiplication? Because this is going to be very important, because if you can get everything to boil down to a bunch of generators, and you know that DR respects multiplication, then you can pretty much compute all of the DRs on all of the spectral sequences in terms of generators. And not only do you have generators in each object, each like abelian group EPQR, but you also have generators in the sense that you can multiply between those groups and get to other groups, which means you could, in theory, generate the entire page with only a few elements. And that actually ends up happening in our example. Okay, so what is the multiplicative structure? It turns out, if you write down all the details, this is what you get. And it is explicitly given by the cup product. Now you might be saying, hey, Max, these are not the same thing a priori. So how are you doing multiplication between them, right? Because your normal definition of the cup product is something like the psi times phi of some chain C is going to be like phi some restricted version of C times phi some restricted version of C, right? And this multiplication happens in a ring. Well, there's actually a cup product between these two guys, which means we can multiply by replacing this product with a cup product, which is why you end up with coefficients in H Q plus Q prime. So what you're doing is, instead of multiplying in a ring to get your cup product, you are multiplying in the cohomology ring to get your cup product, and using this graded multiplication to get a product on the spectral sequence. The upshot that I want you to keep in mind is that if something seems like it should work out in terms of the normal cup product, it normally ends up working out on the spectral sequence. So the product of two generators is usually going to be a generator, stuff like this. Okay, to make sense of this, yes. Okay, and then we have the product on the E2 page, because remember, this is just E2. Well, we have this sign derivation convention. It turns out that this means exactly that the product on page R induces a product on page R plus 1. So in fact, we've figured out all the products. And so this is a multiplicative spectral sequence. And the last thing I didn't say out loud, but was on the previous slide, is that this multiplicative spectral sequence converges to the multiplicative structure on H star E. Oh, I guess I didn't say that at all. This spectral sequence converges to H star E. So what we're doing is we're trying to compute the cohomology of the base space. In fact, the cohomology ring of the base space, of the total space, using the cohomology of the base and the fiber. Okay. One more little piece of setup. So given a simply connected space X with a bunch of trivial cohomology groups, we can create a map F from X to the Eilenberg-MacLane space that is the homotopy group of X at that exact degree. So this is K pi n X at n. Now, moreover, this map will have a homotopy fiber F, and it turns out that this homotopy fiber satisfies this requirement. So what is all of this data telling us? Well, if HKX is 0 for K greater than 0 up to n, then the Hurewicz theorem tells us that pi n X should be isomorphic to H and X. And normally this is easy to compute, so we don't care. Next, it tells us that if we want to compute pi n plus, whatever, Lx, it's equivalent to computing pi k or pi n plus L f, as long as L is greater than 0. So we know that all the lower homotopy groups of X should be 0. We know what it is at n. And importantly, instead of computing all the higher homotopy groups of X, we can now compute the higher homotopy groups of F. This is normally substantially easier. Is there anything else I wanted to say on this slide? No. Okay. Moreover, we can use Hurewicz in the following way. Well, maybe X has something non-trivial at pi n, but F doesn't, which means we can use Hurewicz one level higher and use this, which means that if we want to compute pi n plus 1x, we only have to compute hn plus 1f, which is certainly easier. Moreover, all of the homology groups of F are 0 up to n plus 1, which means we can redo this entire theorem from before, taking a map from F into pi n plus k pi n plus 1 n plus 1, take the fiber F0 of that, and do this whole trick over and over again. And eventually you can compute all the higher homotopy groups of X, right? Because this guy can compute pi n plus 2f, which is equal to pi n plus 2x. So this Serre method basically goes like, let's hope, okay, so importantly, we know the cohomology of Eilenberg-MacLane spaces. And when I say that, I mean that if you really wanted to compute it, it's known how to do it and you could sit down and do it. And if you can speak French, there's this really good paper that like summarizes this conference where they like computed a bunch of them. I don't speak French very well, especially if you look at my transcript. We can compute these guys' cohomology. Let's go back up. So let's say that we know a lot about this and a lot about this. Well, then we can use Serre right away to try to compute something about this. If we don't know something about this per se, but we do know something about loops of k, pi n, x, n, then maybe we can use the previous method to do something about this and try to compute something about this guy. That's going to be our main idea. Okay, so let's move on. Recall that the HKS3 is 0 for 1 and 2. Oh, sorry, this should not be an n. This should be a 3. Giving us a map f from S3 into KZ3, where f is the homotopy fiber, and I'm not going to write the little f anymore. Okay, well, this guy is known, but kind of a pain. This guy is very easy. And it turns out that a fun exercise, KGN, is equivalent to KGN minus 1. This should not be a homomorphism if I'm being, this should be a homotopy equivalence. So if we take the loop space of this guy, we end up getting this. We end up getting this. Now, this is actually very well known. It ends up just being CP infinity. And the cohomology of this guy is also very easy. So what's our current status? We want to compute this guy. We know this very well, and we know this very well. So we can use the Serre spectral sequence and hope everything works out. And this is going to help us compute a higher homotopy group of S3. And in fact, a stable homotopy group because it's only one above. And if you work out the degrees, it ends up being stable. Okay, so let's continue. The computation of Pi4S3. We have finally made it to our goal. Okay, step 1 of doing any spectral sequence computation, figure out what the E2 page is and hope most of the entries are 0. In this case, it's actually going to end up being very good for us. So recall that HK CP infinity is going to be 0 if K is odd and Z otherwise. And then HK S3 is going to be 0 unless K is equal to 0 or 3, in which case it's C. Now, the important thing to note is that a lot of these are 0, which means that when we look at this guy, if the coefficients are 0, then certainly the cohomology is trivial. And if H of S3 with respect to Z is trivial, then it's going to end up being trivial too. So let's figure this out. When is EPQ2 0? It turns out that we need both P to be 0 or 3, or Q to be even, or vice versa. EPQ2 is 0 whenever P is not 0 or 3, or whenever Q is odd. Otherwise, we get a copy of Z. And we actually know a little bit more about this, but I'll get to it in a second. Now it's time for pictures. Okay, so what am I showing you? Each of these pink stems is a point where the sphere will have non-trivial cohomology in theory, and each of these red lines is a place where CP infinity might have non-trivial cohomology, which ends up telling us that the only places where we can possibly get non-trivial results are these intersections here, which is very nice because it means that the differentials have a very restricted window of where they can hit without hitting a 0 and being trivial. So this is actually a very nice example that works out pretty well. Okay. So we're in luck. On the E2 page, most of the differentials are going to be trivial. Why is that? Well, let's think about where it goes. D2 sends PQ to P plus 2, Q minus 1. Now remember our requirements. We have to go from 0 to 3 in terms of P, and we have to go from an even number to an even number in terms of Q. If we don't do that, we're either landing in a 0 or we're coming from a 0. So the only way for the differentials to be non-zero is if we get something of the form like e to 0 some even number into e to 3 some different even number. But the issue is that Q is losing 1, so that's never going to happen. And P is only gaining 2, which means this can never happen. In pictures, we're just missing everything. I actually drew too many green lines. Only pay attention to the ones coming from the intersections we care about. So only care about these ones. All the others are trivially 0. And of course, this goes on ad infinitum. Okay. So on the E2 page, everything is done. So maybe we're in the clear. Maybe we've done all the work. Unfortunately, that's wrong. What happens on the E3 page? So we know that from this example, we know that E2 is going to be the same as E3 because taking cohomology won't change anything because all the maps are 0. But this doesn't happen at E3. In fact, on E3, we get 0 can very easily go to 3 just by looking at this. And Q will always stay an even number if it started an even number. So we do have differentials and we want to know what's going on with them. But on the flip side, if I go back to this page here, or maybe this page here, we also know that at page 4, we're going to be overshooting. So there's no way to have any more differentials. So E3 is a problem, but E3 is the only problem. So you take the good with the bad, I guess. Okay, so before I get into computing D3, are there any questions about what I've just covered?
Could you go back and just show us the definition of the differential of the Serre spectral sequence again? I don't remember.
Okay,
Did you talk about what that was?
The issue is that it's like a connecting homomorphism. I can tell you
Okay,
it
so you're
exists,
just not.
Yeah.
Okay.
And what we're going to end up doing when I say compute D3 is I'm going to do like a proof by contradiction style thing where I'm going to tell you that it has to be this, otherwise there's problems. In fact, I don't actually know what it is. There's 2 options and both are equivalent in terms of computation. But I can't tell you which of the 2 options it is. And I don't know if anyone's actually ever bothered to figure it out. I'm sure someone has. Okay. Are there any other questions? That was a good one. Okay. We will now move on. Oh,
Sorry, there's a question in chat. JP Serre asked, you wrote HN is isomorphic to pi n, but shouldn't it be pi n abelianized? I think we're working with higher homotopy groups, so they're already abelian, right?
That and also, yeah, so the Hurewicz theorem tells you that if x is simply connected, so pi 1x equals 0, and of course pi n x is abelian n greater than 1. The Hurewicz theorem tells you that if pi 1x is 0, and if a bunch of homology groups are 0, then the first time homology is non-zero, you get an isomorphism between pi nx and hnx. But yes, you are right that you do need it to be simply connected. Maybe there's a weaker hypothesis. I don't think so. Okay. But yeah, that's a good question. So this technique doesn't work if you're struggling to compute pi 1. But we have a lot of tools to compute pi 1 compared to pi n. So this is normally not so big of a deal. Any other questions? I can't see chat, I feel like. Maybe, oh, there it is. Okay. Oh man, there's a lot of chat. Okay, looks like we're okay. All right, I'm gonna keep chat open now. I didn't even realize that it was going on. Okay, all right. So here's our visualization, just to remind you that like this is the one and only time where the differentials end up working out so that we can hit like something else that might be non-trivial. So here's our little ladder, and you can see that it's doing the exact diagonal that it needs to. How to compute the differentials. Again, I haven't told you what they are. So right now there doesn't seem like a lot of hope, but if maybe I can figure out some generators of this whole spectral sequence, then it would be easy enough to compute it just on those generators. So we're just going to name some elements first. And I'll show you where these elements live on the picture in a second. So U is going to generate H3S3, and X is going to generate H2CP infinity. What I mean by this is that if you look at this guy who is on E02, it's going to basically end up being, because of how it like H0 works here. So note that this is actually H2CP infinity, which is exactly where the X in this isomorphism lives, which is why I'm using that notation. Okay, and now we're going to do some inspection. The first one that I want to point out is that X to the n generates E302n. And what I mean by that is it lives in E302. So X times X goes to E304 times another X, E306 times another X, E308, so on and so on. It turns out that this is going to remain a generator. The intuition, of course, being it comes from the cut product, it should act like a cut product. Next, U to the K is 0 for K greater than 1. The reason for this is that it starts in, this should be a 3-0. Anyway, it starts in E330, do it twice, it goes to E6 which is like not possible. I'm going to show you again all of this in a picture in a second. Finally, U x to the n is going to generate E3 to n. Now, if you remember, the only ways that these things can be non-trivial is if they're of the form E0 to n or E3 to n. So it turns out we've actually generated everything with just these two elements. And moreover, because the differential on U is going to end up going into the zeros, we only care about the differential on X. So we've taken this infinite number of differentials and reduced the problem to computing only like the differential on one single element, which is pretty cool. Picture time. Okay, so this is where U lives. This is where X lives. If I multiply by U, I'm going right 3. If I multiply by X, I'm going up 2. So, if I start with U and I multiply by X, I end up here. If I multiply by X again, I end up here. If I multiply by X again, I end up here, and so on and so on. So you generate the entire ladder just by multiplying this generator here and this generator here. There's stuff here, but it's not important. Okay. We can now try to compute D3 with only respect to X. And then this is my claim. I claim that this has to happen, and I don't know which one it is. Proof. Okay, now if you remember how we set this up, F has to be very homologically connected. And what I mean by that is H1, H2, H3 of F all have to be 0. Now, what we're computing is going to be H3F. So if you remember, just as a reminder, we're doing, maybe I'll write CP infinity. We're doing CP infinity to F to S3. So we're converging to H star F. Now, H3F must be 0, which means that no matter what we end up with, remember that this is the last page where anything interesting can happen. We're going to need H3F to be 0. Now, imagine that E303, imagine that this is non-zero. That means we get to E infinity and we have something non-trivial on the 3 diagonal, which means that H3F can't be trivial. Like, maybe you have extension problems, whatever. It doesn't matter. It's not going to be trivial. So what ends up happening is that D3X has to kill everything here. What this means is that, so just to write this out explicitly, this is the kernel of dr over the image of dr. This goes into the out of bounds area. So the kernel is everything, which means the image also has to be everything. So D3 has to be sent to a generator, either plus or minus U. So basically what I'm saying is whatever happens after E3 page, we're going to collect all of our results and get our answer. When we do that, H3F has to be 0. If we haven't killed the thing in 3, 0, like if we haven't killed the thing at 3, 0, then we're never going to kill it, which means that we've somehow contradicted ourselves. We have this homologically connected space that also has homology where it's not supposed to. And this is what I meant by you can compute the differentials without knowing anything about them. Okay. Now we know it's a derivation, so we know that it satisfies this formula. You can just work this out on your own. The degrees are all the same, so it doesn't really matter. Like you don't have that sign issue to worry about because it is a derivation. Therefore, we must get the following 4-page. First, everything on the p=0 stem. So if I draw our little diagram, so we have all these guys and then all of these guys. Everything here has to be 0. Why? Because the dr map is injective, which means that the kernel is 0. So when you take cohomology, everything's going to vanish. Here, the kernel is everything, but the image is generated by this guy. What does that end up meaning? Well, if you work out all the degrees, you end up getting this as your result. So these are the only non-trivial modules to worry about. And they're of the form z over n. Now, if you look at these degrees and think about what the diagonals are, each diagonal only has one non-trivial element. So maybe I show what this means. If I take the diagonals, these are the only things that matter, which means that each one only has one thing in its diagonal. So in particular, the computation of this guy is immediate. You just take, what's the simplest thing n can be? 0. Okay, that doesn't matter. What's the second simplest thing n can be? We let n be, we want n to be 2. So put n as 2. This information tells us that E for 3, 2 minus 1 is 1. So E32 is equal to z over 2. And then that computes this guy by itself because you just take 3 plus 2 is 5. Then you pass the universal coefficients. The slogan is that it drops torsion a degree, which gives you this. So we've computed H4 z over 2. And if you remember back at the beginning, this computes Pi4S3 because this is the same thing as Pi4F, which is the same thing as Pi4S3. And so we've computed a homotopy group of spheres. In fact, we've computed a stable homotopy group of spheres, if you know what that means. And I guess one conclusion at this point is that was a lot of work to compute that something is the simplest possible answer, or I guess the second simplest possible answer. Which I hope encourages you to think that these problems are interesting, hard, but also not entirely inaccessible or so abstract that you can't start thinking about them. In fact, I actually can take this method a little bit further. Using some advanced material that I don't want to explain this time around, you can take a space and localize the space. What this ends up doing is it localizes its homology. And if you go through all the computations we just did, it turns out you get even more zeros in homology, which means you can take the computations to even higher homotopy groups. Because remember, it's that connectivity that tells you when you can finally compute a homotopy group. And if you do that, you actually get to conclude that the first time p torsion occurs in pi k s3 is at k equals 2p and is of the form z over p. Now, this doesn't actually compute pi k s3 or pi 2p s3, but it does tell you what the p torsion is. And when we're computing homotopy groups of spheres, we normally have to restrict ourselves to a torsion prime at a time. Because even when you go to more powerful machinery like the atom spectral sequence or the Adams-Novikov spectral sequence, you end up having to work at a single prime. And now I'll give you the exercises and maybe some things to think about. The first is that this is a very good example. I want you to try computing it, taking this and this as given. So you know the homology of these two. Obviously, you know the homology of the middle one already. But knowing the answer is not always a bad thing because it allows you to be sure when you're done or figure out what you're doing wrong. And do this. As a sort of side problem, which I have not tried, can you use this as given instead and compute one of the other two? I don't know how easy that should be, but it seems like it's something that at least is worth trying. Maybe I'll try it on my own eventually. Okay, next choose a nice space X and use the path space fibration in the fact that this is contractible to try to compute the homology of this guy. So a good example is Sn, and I think it does allow you to compute most or all of the cohomology of loops Sn. Finally, use induction and the fibration I mentioned earlier to fully compute the rings H star SUN. As a trick, SU1 is contractible and SU2 to S3 is a homeomorphism, which allows the base case to be easy.
Minute has pointed something out, which is that you have the hop fibration going from S2 to S3 instead of S3 to
Oh,
S2.
I did it right when I hand wrote it, but you were totally correct. Sorry. I knew I was going to miss one typo. I can't believe I got to the last slide and that was where the typo was. That's so painful. Thank you. Okay. Okay, so these are the 3 exercises that I think people can try using only the information in these slides, really. You don't need to know how spectral sequences are constructed. You don't need to read the proof on why they exist. I suggest you don't do that, at least until you've done a few computations. But yeah, I hope I've encouraged people to think that these problems are interesting and maybe give some intuition as to why I think they're cool and why I might want to do like research work related to them. Are there any final questions? All right. So before people leave, I know that Zoff is going to give a talk on monstrous moonshine. I don't know when he's going to be ready, and I don't know if he's currently here yet. But if he isn't, I would just
Can you hear me?
Oh, yeah. Perfect.
Okay, I just got here, so perfect
Oh,
time.
nice. Wow, I did that perfectly.
Okay,
I totally had that plan. But yeah, I'll turn it over to him. Thanks, everyone.
Yeah, maybe you can
stop
answer
sharing.
some questions as I set up.
Okay, cool. Yeah, I'll take questions.
And I think you have to make me a host as well.
Oh, yeah. You and Brent. Okay. All right. Yeah. Carl, what's the... Never mind. Oh, all right. Oh. Okay, yeah. So I know very little about this. It turns out that, actually, hold up. Let me bring up my notes on this just so I say things that are true. Yeah. Okay. So you have this J homomorphism, which basically splits up the homotopic groups of spheres into computing the image of J and the co-kernel of J. And it turns out that if you want to compute the image of J, then these Bernoulli numbers end up coming up in the sense that, okay, just to read it explicitly, the order of the image of J at degree 4k minus 1 is the denominator of bk over 4k, where bk is the kth Bernoulli number. If you want an intuitive explanation for why this is true, I don't have one, but just know that like there are a lot of ways to break up the homotopic groups of spheres to make computing them easier, one of which is this J homomorphism. And it turns out that I'll answer that in a second, Nicole. It turns out that this J homomorphism's image is actually very heavily dependent on these Bernoulli numbers. And in fact, if I'm remembering correctly, and now I'm talking off the cuff, I think this is also related to the covariant invariant problem and like which of these are non-trivial and stuff. Oh yeah, because there's like the image of J comes up in that too, so that's where that comes from. Okay. So I'm going to stop the sharing and I'm going to stop the recording.